Now in this lecture we are going to discuss group theory. Let us begin with semi-group. So for all these semi-group, monoid and group, so we are going to use a set, let's call it as A and an operator, okay. So this star is not multiplication or addition or anything, concatenation. So this is a abstract operator, okay. So this can be anything which satisfies following conditions we will see. So you have a set, that set can be integers, otherwise any set of symbols, okay. Now let us try to understand semi-group. So such set comma such operator is called semi-group if it follows these two rules. From now onwards you remember, these definitions are very important, you remember them because the theory begins here. So star is closed. Sir, what is the meaning of that? So whenever I say an operator is closed, then take any two elements a comma b, then if you apply a star b, then you get an element called c, let's say, then that C is also a member of A. Then we say that this operator is closed. That means when you take any two elements and if you apply an operator between them, then the result will be part of the set. Okay. Example, let us take natural numbers comma addition. You take any two natural numbers and you do addition like 1 plus 3, 1 plus 1, anything, you get a natural number back, right? So that is the meaning of closedness. Second thing, for every three elements, so this is associative rule. Associative rule holds good. A star B star C equal to A star B star C. Now don't worry about the operator's meaning, forget about that, whatever the operator it is, this should be satisfied, okay. Now we say that such set along with that operator is a semi-group. Let us summarize. So whenever I say A star is semi-group, so star is closed, second one star is associative, okay. Now let us talk about monoid quickly. So monoid is A star where star is closed like semi-group and associative, star is associative, fine. That means so far monoid is semi-group followed by extra condition. What is that extra condition? There exists an element E, I am just showing symbolically E. So because this has a particular functionality, we will see that. So this is one of the element in A, so that such element star A equal to A star E equal to A for every A belongs to A. Okay, so there should be one special element E, I am repeating. If you apply a star between that element and any element of your set, then what should happen? Same element should come back. Example, let's say E is an element. Whenever I say E is that special element, then E star B should be what? B. E star C, C. Similarly, C star E, C. If any element has that property, then that is called actually identity element. Okay. So finally in monoid we have identity element, okay. There should be at least one identity element, right. So this is about monoid and semi-group. Now after that we will see group, okay. Now we will talk about group. I am using a different symbol G because I want to represent group. So G is closed under star, same like previous one. For every three elements associative rule should hold good, yes we know that. So that means your group should be semi-group. There exists one identity element such a way that, of course, that is a property of identity element. I should not say identity element. There should be one element, at least one, so that E star A equal to A star E equal to A. Then we say that that is identity element, of course. But this is a rule. Remember it. Okay. Such an element, if you can show, then we say that such thing is monoid. Then after that, the new condition you say, for every element belongs to your G, there should be at least one element belongs to G. This is just another element, that's it, okay. For every element I should show some element so that A star such element A inverse should be such a way that A star A inverse equal to A inverse star A equal to E. Such an element if you can show, then we say that that element is called inverse of A inverse is called inverse of A, okay. So A inverse is inverse because not because of this model or structure, it is because of this property, okay. Sir, can I understand it like this? How? I have an element, sir, B, and I have A. I applied A star B and I applied B star A. I got A star B equal to B star A equal to E, where E is identity element. Then can I say that B is an inverse of A? Yes, then B is called inverse of A. Now see, whenever A is, B is inverse of A, automatically B is an inverse of A. Sorry, A is an inverse of B. Why? Because see, same thing. I am proving that A is an inverse of B. Why? Because take B now. For B, if you apply B star A or A star B, what are you getting? E. That means what? For B, A is an inverse, correct? So that's why I can say that whenever for A, B is an inverse, for B automatically A will become inverse. It is easy to understand. Okay. Now, so let me summarize. A group is nothing but closed, associative, there is identity element, there is an inverse for every element. So if you remember these four rules, then that's it. So remaining theory we can slowly understand. So what I am going to do now, I take one example and we will see whether it is a group or not. Let us take randomly natural numbers and an operator now addition. You know addition, right? Yes. Let us begin. The first step what we have to do is we should check whether it is closed or not. Take any two natural numbers and if you apply addition operator, you get same another natural number, correct? So closed, fine. So first condition is done. Second condition, what is that? Associativity. You know that, we are not proving associativity. I am not proving, but we already know that. What is that? Addition is associative, correct? So in your childhood you have studied, otherwise you remembered it like this. 2 plus 3 plus 4 is nothing but 2 plus 3 plus 4. But proving is not a big deal, but I don't want to waste the time now. So remember it. That's not a big deal. The third thing, so we have to show identity element. Is there any identity element? What is the property of that identity element? E star A equal to A star E equal to A. Here star is plus, right? Let us take. We have to prove that if we have an identity element, let's call it E, then E plus A equal to A plus E equal to A, correct? Can you show such element? See, natural numbers means what, sir? Can I include 0? Let us include 0 also. Yes, natural numbers can start from 0. So, and they can also start from 1. It's up to us to, fix it. So, natural numbers are defined in two ways. Natural number starts with 0, 1, 2. This is one old way. Now, in modern numbers, people use 1, 2, 3, so on as natural numbers. Okay. So, that's why. Let me take this one as natural numbers. So 0, 1. Natural numbers means counting numbers, right? So counting numbers should have 0. Why? If you don't have 0, how you count everything? Example, let's say I have no mangoes. Then how many mangoes I have? 0. Correct? So that means to count really natural numbers are counting numbers, then definitely it should have 0. Correct? So it's better. Like I am not saying that this is not set of natural numbers, but this is what drives me to assume that natural numbers as 0, 1, 2, 3, so on. Okay. Now, E plus A equal to A plus E equal to A. Can we have such kind of number? Well, let us check. My guess is 0. Okay. It's just trial and error. That's it. 0 plus A equal to A plus 0 equal to A. Correct? Yes. Yes. So 0 is an identity element. Now we'll come to the fourth one. For every element, you have to show what? Inverse. What is the property of inverse? We know. Let me write it first. That's why always whenever I try to understand something, first I start from definition. So if you want to find out inverse of an element, then first try to understand what is inverse. Example, let's say inverse of A is A inverse. Okay. Then what is the property? A plus A inverse equal to A inverse plus A equal to 0. We should show it. Such an element if you show, then we can say that there is an element inverse. Okay. Let me take a random variable A plus its inverse is A inverse. A plus A inverse equal to 0 in mathematics. See this is addition operator. So A equal to what? Minus A inverse. That means yes, A has an inverse, but that inverse is nothing but minus of A. Correct? So otherwise you write like this: A inverse equal to minus A. Correct? Yes. But we have only positive numbers, correct? Otherwise non-negative numbers, we don't have negative numbers, then such possibility will not arise. That means so there is no inverse for some elements, correct? So it's easy to see now with 2. For 2 plus dash is 0, minus 2, correct? So yes, there is an element which satisfies this condition, but it is minus 2, which does not belongs to our set. It should belongs to our set. So that's why this condition is violated. So natural numbers doesn't form group with respect to plus. Remember it. Sir, is it not monoid? Yes, it is monoid. Let us take one more example. Multiplication. 1 minus 1 and multiplication. Is it a group? A very small set. See, my intention is writing set, okay? Don't get confused. So, set is 1 minus 1, operator is multiplication. Let me use this one. First step, is it closed? 1 into minus 1, minus 1, minus 1 into minus 1, plus 1, 1 into 1. You have to check every combination. 1 into 1, 1 into minus 1, minus 1 into minus 1, minus 1 into 1. Yes, I covered everything. So, all are closed. That means you are getting same element, element in the set. Second, associative. Yes, multiplication is associative for very large numbers, even real numbers. If you take all the real numbers also, your multiplication is associative. Then after all, for these two elements also will be associative, correct? From now onwards, you remember, when you know that for some bigger set, some symbol is associative, then for subset also, if I take any subset, for that also associative rule holds good, because for bigger set associative rule holds good means what? For any three elements, associative rule holds good. Then for some elements also associative rule holds good. So this is like this. Example, every lion drinks coffee. Then there are some lions, female lions. Do they drink coffee? Obvious, right? If every lion drinks coffee. So that is the way we can understand that for 1 comma minus 1 also, associative rule holds good. Now, third one, there exists E belongs to G. We have to show the identity element, right? Now, by that time we got experience now. Let us go fast. So, what is the identity element here in 1 comma minus 1? What is the property? So, A star E equal to E star A equal to A. With my knowledge, I understand that 1 is identity element, because 1 into 1, 1 into any element is, take 1 into minus 1 is what? Minus 1, correct? Yes. So, 1 into 1, 1. So, that's why A star equal to A. So, that's why there is an identity element. Now, inverse. You have to show inverse for every element. For 1, what is an inverse? 1 star, that inverse element, let us assume that as x. 1 star x equal to x star 1. Don't get confused. This is multiplication now. Okay. 1 into x equal to x into 1 equal to 1. Right. So, what is that element? 1, see, correct? So, yes, 1 has an inverse. Now, minus 1. Minus 1 into that inverse equal to dash into minus 1 equal to 1. Can we have such element? Yes. Minus 1 into minus 1 equal to 1. So, minus 1 has inverse. So, yes. So, this 1 comma minus 1 forms a group, right? Because it satisfies every condition. So, in the GATE exam, they give you one set and an operator, they define it. If it is new one, then they ask whether that set forms a group or not with respect to that operator. So, we will see so many examples, so that with experience you can solve every GATE problem related to that model. Okay. Now, we will see one problem. Consider the set H of all 3 by 3 matrices of the type AFE 0BD 00C, where A, B, C, D, E, F are real numbers. Find ABC not equal to 0. See, this diagonal contains ABC, right? Their product is not equal to 0. I will tell you the reason why they have given. So, the question is, under the matrix multiplication, H is what? Is it a group or monoid or semi-group is a question. Now, we have set of rules. We blindly follow them. First thing, we have to prove that this matrix multiplication is closed, correct? So, let us take two random elements. Okay, not particular elements. We know how to take it, right? Let us take like this. AFE 0BD is one element, 00C, and you multiply it with another matrix. Let us take other variables rather than this AFE 0BD 00C. So, what we do is A, B, C, D, E, F, right? We take from G, G, H, I, 0, J, K, and 0, 0, L. You multiply them. So, you know matrix multiplication, correct? So, when you do that, you realize that you get again same structure. So, that means if you get same structure, then so that kind of structures already belongs to H. So, that's why we can prove that. So, such elements belongs to H. Sir, but you took only two elements. No, this represents any element, this represents any element, because we have taken variables rather than a particular values, right? If I take particular values like 1 2 3 4 5 6, then my result whatever I get will be restricted only to particular values, but I am not taking particular values, so it is closed. Sir, why are you not doing multiplication? It takes a lot of time and unnecessary, right? Even you know how to do multiplication. So that's why I am not doing it. Second thing, associativity. Already I told you, for all set of matrices, if you take 3 by 3, then they are associative, correct? Then some of them, this kind of structures are some of them. So they also will be associative, already I told you, right? Second one is done. Third one, identity element. So did you remember in whole group of multiplication, what is matrix multiplication? What is identity element? Please recall. It is 1 0 0 0 1 0 0 0 1. This is the identity element, correct? Now see the structure. But is this structure belongs to our set? We will see. Yes. A, B, C, 0, D. Yes. Actually, see the structure. It is A00. Yes, A00. Then FB0. Yes, FB0. Yes. Then EDC. Correct. So here the only thing is here you should have zeros. That's it. Remaining elements can be anything. Don't say, sir, why we have 0 here, but here we have non-zero. Who said f is non-zero, right? F can be 0. That's why. So the only thing you should see is here 0 0 0 we should have. Yes. So identity element have this structure. So this belongs to our H. So and it is identity element for total matrices. Then here also it will be identity element. Correct. What is the property of identity element? Recall. You take any matrix A. Right, if you multiply with identity matrix I, you get A. This is true for all the matrices, then this is true for this set of matrices also. That's why you don't need to check. Now the fourth property is inverse, right? You take any matrix A, so A inverse equal to adjoint A by det A. So here adjoint A exists for every matrix. Only det A has a problem. If det A is 0, then A inverse cannot exist. We know that, right? But how can you say that this set of matrices have well defined det A? Yes, we can easily prove. Please remember, any upper triangular matrix, if you have, you take any upper triangular matrix like this, it's the product of diagonal elements here ABC is going to be det A. So ABC not equal to 0, that's why it is given. So that's why here determinant A equal to ABC. So it is not equal to 0, then A inverse always exists. Now for every element, that's why A inverse is well defined. So this is a group, correct? Right. Here I am using a point that for upper triangular matrix like this, det A, that means determinant is A into B into C. Okay.